Okay, two kinds of threads that we have to uh, talk about. Number one is about the hardware threads. Generally, we talk about hardware threads are nothing but your logical processors. We can also call it as a hyper threads. So we talk about the physical CPU core. That's what the hardware threads. Right. And the second thing we talk about the system threads. System threads means these are the logical execution units. Those are all managed by your operating system scheduler. Operating system scheduler. So generally, whenever we are talking about threads, whatever we are talking about threads, we generally talk about the system threads, which are the operating system threads. Okay, not the hardware threads. And then what happened? There is something called multiplexing. Multiplexing is something like there cannot be an unlimited number of hardware threads. Of course, there are 8 core processor. There could be only few threads, few hardware threads. But when you look at your computer, there could be thousands of threads that are running on your computer. The simple example, if I go to my uh, terminal, I can put a command called top. Sorry. You could see that top command. You could see that I have got only 12 core processor on my machine. That means my hardware threads are only 12. But if you see that for about 3700 or 800 threads are running on a 764 processes. You know that each process contains one or more threads. However, there are for about 3750 threads are running. All these are multiplexed. These many threads are multiplexed against the 12 core processor, 12 threads. Okay. So what happened whenever you create a thread in any programming language? Let's talk about Java or even P threads in C, C++. What happened when you create a thread? When you create a thread, automatically whenever you create an application and the application is running, you get a thread. Of course, each and every process contains at least one thread. But what happened when you create a thread? What I mean to say, when you additionally create another thread, when you add another thread, let it be it's a multi-threaded application. When you create a thread, your application is running as a process. So your application would be one among these processes if it is running, and then the application would have two threads. So the threads would be one among these threads, those two threads. But the problem here is threads are managed by your operating system. That's the most important thing. Threads are managed by your operating system. Threads are not managed by your programming language. Even in Java, if you talk about a thread, threads are managed by your operating system. I think very long ago, even I didn't use Java. Java has moved from system threads to some green threads, but it failed somewhere and then it went back to the system threads. Okay, what are called green threads? I will explain about green threads. But whatever you see, threads are managed by your operating system. That means every time your application has to create a thread, has to pass a thread, resume a thread, or the context switches from one thread to the other thread, or the scheduler stops, pauses your thread, goes to the other thread somewhere else running, and comes back to your operating system, your application, sorry. Everything is handled by your operating system. There is absolutely nothing your programming language to do. That means even you say that thread, new thread or span a thread and all, these are all you are telling operating system from your programming language. You're telling your operating system. So that means behind the scene it may call a C language wrapper, libc or glibc or something, because that has to make a system call. So here the concept is every time you create a thread, every time the thread has to be stopped and resumed along with many other threads in your operating system. Everything is handled by your operating system. If the thread is paused, generally each thread is paused for 10 milliseconds. I think, or after 10 milliseconds, the thread loses a context. For example, I'm telling there is a scheduler. The scheduler schedules for every 10 milliseconds, or for every second 10 milliseconds is passed, whatever, because it gives some time slice. So it runs so fast that we can't see that. 10 milliseconds looks pretty small time, but with respect to threading, it's a pretty good time. That means threads run so fast that we can't see how fast things are running. Okay, so the threads are managed by your operating system. Every time your application has to stop a thread, the thread gets paused, it is done by your operating system. So your application has to seamlessly talk to your operating system. That is the most important thing. So there is a latency. Every time your application has to talk to your operating system, there is a latency. Okay. So we have OS threads and then hardware threads. OS threads are done by your operating system. Hardware threads are managed by your hardware, whatever it is. Fine. So here there is a concept of context switch. There is a concept of scheduling. If you look at any process, a process means here when I run top command, sorry, when I run top command, these are all processes. There are these many processes are running. What is a process? Process is the unit of execution. Basic unit of execution is called a process. When you look at the process contains so much of information, but I can talk about uh, uh, some information which is required. We already discussed, I guess, a process contains some memory. Of course, process contains ID, process ID, status, whether the process is running, paused, or something. And the process also contains resources. Resources, maybe files are opened or network sockets are opened. The resources process contains. Generally, what process contains, it depends on operating system to operating system. But I'm writing in a generic way. That means where the file is opened, what is exactly the page number or reference to the pages inside your SSD hard drive, hard disk. All these things are being managed by your process, and it contains memory. We already discussed about memory. The memory contains code or text segment, data segment, stack, and heap memory. So code or text segment is used to load the binary itself. Data segment, you know that this memory is allocated but would not be deallocated. There is no mechanism to deallocate the memory. Generally, all the global variables, package level variables, or even the static variables in other programming language, they are all stored in data segment. Stack and heap memory, we already saw. Stack memory is the memory uh, that gets deallocated very fast based on the scope. Heap memory is the memory that is managed by your garbage collector in Go language or C Sharp or Java. However, the most important thing I find it here, I feel like that is going to be the most important thing is the program counter, stack pointer, and registries. The process contains program counter. This is very, very important. Program counter, because every process has got stipulated amount of time that is given by your scheduler to run, because there are only 12 on my machine, there are only 12 hardware processors. These hard all these threads that we run are not actually hardware, they are all software operating system threads. All these threads have to run on they have to run on uh, a fewer number of processors. That's what the multiplexing. So the program counter, that means there is a context switch happens. Okay, there is a scheduler, the schedule sometimes the scheduler operating system has got a scheduler. The scheduler gives us a stipulated amount of time to execute. After that, scheduler passes that particular thread and then it goes and picks the other thread. A simple thing, you make a call to maybe any e-commerce site. Let's say you make a call to Amazon, you have some issue with Amazon order. You make a call to Amazon. You explain about your issue to Amazon. You have been talking about what went wrong with Amazon, what went wrong with your delivery. You explain that. In between, the call got cut due to XYZ reasons. The call got cut. The reason could be of anything. Maybe you were traveling, though there was no signal, or your mobile got charge was over, money was over, is over, or whatever happens, or even the other side, the call got cut and all. Again, when you make a call, what happens? The call is not given to the same person. The call is generally given to the other person because how that is how the customer care works. There are hundred or even thousands of people are working in customer care, so probably it is less likely that the same person picks the call. And then what happens? Generally, olden days, maybe I'm talking about 7 8 years ago, you need to explain the problem from the beginning. You have to start from the beginning. Hey, uh, this is what I am. This is what I booked. This is what I received. Whatever the issue you have got, you need to start from the beginning. What does it mean? That means you have to repeatedly tell the same thing for every time you connect to the customer care. So they are not maintaining the state. If the call is dropped, okay, they have no idea because the call gets connected to another agent. There is no idea what you have been speaking about. That is a big problem actually, which we call it as a state. So what happened is when the thread gets the context switch going from one thread to the other thread from the operating system perspective, the thread that where it has left off or the thread that has put on hold or paused and it comes back, resumes back to the same thread, it should have the information where it has left off. This is where the registers comes into the picture. Generally, we think that registers are for the hardware. Even your process, even your process maintains these registries. These are all dummy registries. These are not original registries of your process, but they maintain registries. These registers maintains the values where it has left off. And then there is something called PC, which we call it as a program counter. Stack pointer is about the uh, uh, where it is in the stack, what it is accessing in the stack. It is always on the top of the stack, so we call it as a stack pointer. We are talking about the PC, program counter. According to me, the PC is the most important thing. Again, these are all software related things, nothing to do with your hardware. So the program counter always gets what is the next execution that it has to execute. Program counter gets the information about what is the next execution it has to execute. Okay, that means whatever the ongoing execution, because execution in a processor is very, very minute step. As I said earlier, let's say I have A, B are two variables, and then I created a equation, for example, a dummy equation, maybe A plus B whole square. Okay, A into A plus B into B plus 2 into A into B. If you look at this particular expression, this whole expression is not evaluated in a single instance. If it is evaluated in a single instance, we can talk it as an atomic operation. But this whole expression would not be evaluated in single instance. How the expression is evaluated, it's purely based on the operator precedence. The operator precedence starts from left to right. So it because multiple operators has got the same precedence, so it takes from left to right. So A and A are evaluated. When you look at the processor, according to microprocessor, this is not a single operation. This operation is a very, very multiple operation. Let's say multiple. Maybe I'm just giving maybe R3 AA. Generally, this is not the case. Okay, fine. R3 R3 is AA, for example. So A into A is stored in a register called R3. Okay, then multiple R4, for example. I'm just giving, for example, B and B. Multiple of R5 is, okay, 2 into A. Multiple of R6 equal to B and then R5, because this is the expression that it has to. So these are all the registries that get stored, right? And then you have add operation. This is where R, maybe R3 is R3 and then R4, and there is an add operation again R3. I'm just giving you some R3 and then R5. I'm just giving you the pseudocode, not exactly the code. Add of maybe R3 is R3 and then R6, and maybe you get the result into R3. Fine. For example, these many operations happens with respect to the with respect to the processor. The process may be halted at any operation, so the entire e- uh, expression would not be resolved at once. The processor may be halted at any point of time. Okay. So what happened? Two things it has to do. Why I'm talking about is we are getting into the Go routines way of doing things. For that, you need to have at least some information. So this is a pseudocode. I exactly don't remember exact operation, but I'm just giving you. Assume that these are the registries. Actually, there are only two values. However, fine. I think you have to use move operation and do the things before going to do that. I think it could be something like this. Move of maybe R3 of A and multiply of R3 into A, something like this. There are only two values, not three. However, so the most complicated, so this is where the expression is. According to your high-level programming languages, this got to be the expression. But when this is turned into a microprocessor, this expression would become multiple multiple statements. Sorry, multiple instructions with respect to the microprocessor. So the program counter always keep an eye. Okay, this has executed this. What is going to be the next? This 24 is going to be the next. It contains the next information about the next operation. So for example, context got switched. So whatever the time that is given to this particular thread is past, it is over, then the scheduler schedules the other thread. That's how the it's called actually primitive threading. Primitive threading means every thread is given stipulated amount of time to execute. Then what happened when the time elapses, automatically it picks the other thread to execute. It is done by a scheduler. Scheduler is a component inside your operating system. So it schedules. By the time it schedules, how does it know that what is the next instruction when it comes back? How does it know that what is the next instruction to execute? Because it has left from that this particular thread to the other thread. How does it know that what were the values? Because it has already calculated when it left this particular expression, it has already calculated, for example, multiplication of R5 B into maybe B into B. This is where actually the registries comes into the picture. Number one, the program counter. It has got all information about what is the next execution, next instruction that it has to execute, and the registries. These registries are with respect to process are not exactly the registries of your hardware. Hardware registries are different. These are the dummy registries. These are still the software registries. So when it comes back, all the values are stored inside the same registries, these registries. So it knows that where it has to go, what is going to be the next instruction, It also knows, it means the process also knows that what are the values in R3, R5, R4 when it has left actually executing this. That's the reason atomic operation somewhere it's very important, particularly in multi-threaded application. Or we also write mutexes and all to lock actually so that multiple threads do not try to access the same variable. Of course, for it's a different purpose, still we use the locks. This is the information. So context switch means the context is switched from one thread through the other thread. The values are preserved in registers. I'm sorry, I don't know. I'm getting registers. This is what the context. These are the dummy registers. These registers may be different for different operating systems. All the information is not same for all operating systems. Generally, the PID, process ID, and then the date memory, these are all generally same, but the internal information about a process, every operating system or the version of the operating system could have some additional information. But at a high level, this is the concept. This is called preemptive threading. Preemptive threading means every thread is given stipulated amount of time, which we call it as a preemptive threading. There is another concept called cooperative threading. Cooperative threading means, for example, you are standing in a queue in a bank. Your turn came, and then you are speaking to the banker. You forgot to fill some information. By the time you understand, at that time you understand that you have not filled some information. It takes maybe 10 minutes to fill the information. Do you still stand in the queue to fill the information, or do you move aside so that you let the others do the work? Actually, the concept is generally speaking, we move aside. Okay, we move aside. We cooperate with others. We don't block the queue. We move aside. Similarly, threads also do the cooperative threading. Cooperative threading means a thread understand that okay, it's going to be block. It's going to block. It let the other thread to run rather than blocking the thread. Blocking the thread is wasting the time because cooperative threading is not based on that. Cooperative threading happens based on the time slice. But operating system go for primitive threading, irrespective of whether the thread is most of the cases. Okay, there may be cases where it also done the cooperative threading. Most of the cases, I'm talking in a general terminology. So, what is the problem here exactly, and how the Go is going to solve this particular problem? The problem here is there is no problem. It is working perfectly. All other programming languages are using the same concept. But the problem here is every time your application has to talk to your operating system kernel by making a call to the kernel libraries. It requires more memory, ask the kernel. It has to be passed and stuff like that, ask kernel. The thread has to be created, ask the kernel. The thread has to be removed, span or removed, join the threads. I mean to say, in the last, everything it has to talk only to the operating system. Anything with respect to the thread, it has to ask or it has to tell the operating system. This is a little cumbersome job because it increases a lot of latency. Latency gets increased because of this particular issue. Because the more the calls to the operating system, the more latency it is. Latency should be something that has to be less in number, but it increases the latency. I'm not saying that others are not using it. Yeah, but when you compare it, there is an issue with the latency. Okay, fine. So how Go does it? Go does it Go solve this particular issue by bringing its own scheduler. Number one, Go runtime has got its own scheduler. First of all, how Go achieve this? Go achieves that through green threads, which we call it as Go routines. You have you ever heard about uh, what do you call? Yeah, we discussed about CSP. We discussed about communicating sequential processes. So Go uses CSPs for the threading and then sharing data between the threads, communicating sequential processes. However, Go uses a concept called green threads, which we call it as Go routines. What is the specialty of Go routines? Because of bringing the Go routines, the call to the operating system are brought down to fewer number. Okay. Generally, there is as we already discussed, there is MS to N multiplexing. The MS to N multiplexing is the hardware threads is to the software threads. That means the OS threads. But here there is MS to N happens. Assume that M is Go routines. M is operating system threads. N is Go routines. Again, the multiplex happens. But who maintains the M and M here? N is the Go routine and M is the system threads. That means Go also uses the threads behind the scene. It is somewhat similar to thread pooling. You know, you might have heard about thread pooling. Why do we use thread pooling? Because creating threads, managing threads is a costly affair. So for every request that comes to your web, for example, you're talking about a web server cannot create a new thread always and execute the thread, the call and then remove the thread. It's a pretty costly affair. So what it does, it uses a concept of thread pooling. That means a pool of threads are already created and then they are ready to cater. Whenever the request comes, one of the thread is picked from the pool and then that particular request is handled by thread. Okay, if the number of threads are 10, for example, you cannot generally technically you can create thousands of threads, but operationally it is quite cumbersome. So that's the reason always the thread pooling is 10 threads or 20 threads, something like that. It's not 1,000 threads. Because the threads are already created and they are in the pool, what happens whenever the request comes? A thread is already available, thread is picked. That's what it happens in generally. But here, everything is done by Go routines. Every request that hit your Go application, if it is a web application, that request is handled by Go routine. How Go routines are very fast? Go routines are very small in size. Number one, they are maintained and managed by Go runtime, not by OS. They are scheduled by Go scheduler, not by OS scheduler. For example, Go routine requires, sorry, okay, for example, a thread wants, assume that each thread is getting 8 MB of memory. For example, exact number, I think 4 MB or 2 MB it gets. It depends on operating system. Every time a new thread is created, some memory is allocated for the thread. Assume that 8 MB of memory. So the code that you write inside the thread, it start consuming the memory and then or 8 MB and it requires another maybe 10 bytes. Then your application asks the operating system, hey, I want more memory because my thread has consumed all the memory. I want more memory. The moment your process asks for more memory, the operating system would not give 10 bytes that is required. Rather, the operating system gives you an additional 8 MB. But your requirement is only 10 bytes, but it gives you additional 8 MB. But Go, what happened? The memory, generally each Go routine is for about 2 KB. 2 KB is very small amount compared to 8 MB. 8 MB is a hypothetical number. Exactly, I think it is 4 MB or 8 MB. Generally, it is multiply of 2. That's how it works. But however, okay. So what happened? The requirement, memory requirement is based on the memory is given based on the requirement instead of chunk of memory. So 4 MB is 10 bytes are required, 10 bytes are given. And then this should not be called or talked to your operating system. It is taken care by your Go runtime. And the context switch is also managed by Go runtime. Because the context which happens between Go routines. See, behind the scene, threads are running. But with respect to your application, there are two things. With respect to your application, everything is taken care by Go. Everything is taken care by Go runtime. The runtime, Go runtime. Whenever you run an application, runtime is created. That runtime handles all the things. Because of all these things, what happened is the calls to the operating system are minimized. Doesn't Go call the operating system kernel? Yes, Go runtime uses behind the scene threads, but Go routines, thousands of Go routines can run concurrently. Whereas to run thousands of threads for an application inside a process on an operating system is operationally very critical. But you can easily run thousands of Go routines seamlessly. I ran actually not even thousand, I even more than that, half a million Go routines I ran in one of my application. Seamlessly they run. But can you believe to run half a million threads? Forget about your application. Your whole operating system itself is not running more than 4,000 threads when I checked it in my computer by running top command. So technically it may be possible because it's all about how much memory you have got, but operationally it is not. It creates abundant latency. Your application becomes very sluggish. Sometimes it gets crashed. The reason if it is doesn't find required memory and whatever it is. So number one, Go routines are green threads, very small in size. Number two, they are all managed by Go runtime, not by operating system. Number three, like operating system scheduler, there is also a Go scheduler which takes care of the Go routines. Number four, the memory that is given for each Go routine is pretty small. Whenever it requires more memory is allocated. Whenever it requires less memory, again the memory is that is given to that particular Go routine is brought down. Always memory is given based on the requirement. The context which happens between the Go routines is also taken care by Go runtime. So here the question, why Go routines are very fast? The straight away answer is Go routines are very fast because Go routines are not run by Go operating system, rather it is run by Go runtime. But right now, if you look at execution flow of a Go routine, the first thing is when you create a new Go routine, we first of all, what happens whenever you start executing your application, Go runtime creates the number of threads which are equal to number of number of cores. I have 12 core processor. Go creates 12 threads. We don't call them as threads. Actually, with respect to Go, we call them as P. We name them as P. Each thread has some additional information. So it is called as P or process. I'm not talking about uh, the application process. I'm talking about inside Go runtime. They call it as a P. Why not thread? Because it contains more than thread information that is more than thread. So every time a new Go routine is created, every time a new G is created, when new G is created, so here G means Go routine, P means a thread plus additional information. So we call it as a process, and then M is to N, multiplexing and all. Every time a new Go routine is created, okay, it is placed on a local, it is placed on a queue basically. Okay, it is placed on a queue. So we call it as a global queue. So every time you create a Go routine, a new Go routine, every time a new Go routine is is created, it is placed on a global queue. The queue is maintained by Go runtime. It is placed on a global queue. These implementations are little different for different versions of Go. Okay, earlier it used to maintain only one queue, but later on it becomes global queue and local queue, etc. Every P contains a local queue. That's why I said P is not only thread, P contains much more information than thread. P is what? Process. What a process contains? A thread. So how many P's are created? On my machine, 12 P's are created for every when I run Go application. That means 12 threads are created. Why I'm not calling it as a thread? Why I'm calling it as a P? Because it contains more information than thread. So I call it as a process. They call it as a process. What does P contains? P contains a local queue and additional information. So things go into the Go routine global queue. If a new Go routine is created, one of the P's picks that particular Go routine. It could be round robin, or it could be the whichever the process is running fewer number of Go routines. Exactly. Again, the algorithm changes, keeps on changing. I guess initially it was round robin, but later on it got changed and all. Then the new Go routine goes from global queue to the local queue. Global queue is a queue across all P's. Local queue means each P contains its own local queue. What is P? P is assigned OS thread. So the P picks a Go routine to execute from the local queue because already things came from global queue to the local queue. So if the local queue is empty, that means all the Go routines that it has to run, they finish at execution. Then it tries to look for are there any Go routines that are created and placed on the global queue. If there are, then it goes and picks from the global queue. If they are not, it may sit idle because there are nothing to execute. So ultimately what happens? This P assigns all these Go routines on an operating system thread behind the scene because P is nothing but an operating system thread. Additional information than a thread, that's the reason we call it as a P. How long the P executes the Go routine? So long as it is blocked or it is finished. For example, if the Go routine is doing the IO operation or network IO operation or file IO operation, there is a chance that the Go routine could be blocked, or the Go routine is blocked, or the thread also blocked because file IO operation, network IO operation are low level, so the thread handles them. because your operating system doesn't know anything about your Go routine, it knows only about threads. The operating system contains information about threads, not about Go routines. Then if the P is blocked, okay, it it goes and picks another Go routine from the local queue. It's blocked, then we let it be blocked. It goes and picks another Go routine. So each P has got a local queue of the Go routines. For example, P goes out of the work, it goes and picks, steals Go routine from another P. There was another algorithm, work stealing. There is another algorithm got added which is called a work stealing. Work stealing means if the P is free, one of the P's is free, then it goes and picks the work from the other P's, because there are 12 P's on my computer, because 12 core processor. When I run a Go application, there are 12 P's are created. So it goes and picks from the other P, which we call it as a work stealing, and also load balancing. So workload gets distributed across multiple P's. What if the Go routine, as I was telling, what if the Go routine blocks the IOOS thread? For example, I have 12 Go routines, 12 are placed on 12 different P's. They they block the thread due to some reason. They are performing some operation. Maybe a concurrent IO based operation is running. They block the thread. That means ultimately behind the scene they block the thread. If the thread is blocked, everything, all the Go routines on top of the thread also gets blocked. Then what Go does is, if none of the P is free, it is blocked. Go runtime, it may create a new P. Basically, by default, there are 12 P's are created on my system because I have 12 core processor. If all 12 P's are blocked, it goes and then creates a new P. That means it creates a new thread basically. It creates a new thread. Okay, so that's how actually all the Go routines work seamlessly. Go routines are very efficient for the CPU bound tasks. There are certain things like IO bound tasks and CPU bound tasks. Go routines are lightweight because it has got very small memory footprint compared to OS threads. Actually, the Go runtime handles the creation of the Go routine, scheduling, and the context switching for all these things. Particularly, the threads gets blocked for the IO bound task, and then it may be waiting on operations. The switching and all happens by your Go runtime. For the CPU bound task, that means it's a too much of calculation is being done. Let's say you are reading and writing to a file heavily, then we can call it as a IO bound task, maybe network IO or file IO. When you're doing a lot of calculations, we call it as a CPU bound task. For CPU bound task, primitive scheduling ensures that the whatever the loops that are given are periodically interrupted, because it's a loop, it keeps on executing something periodically interrupted. That means every 10 milliseconds, for example, it interrupts so that the other Go routines can run. It's a primitive scheduling. I'm talking not from the OS thread, I'm talking from the Go routines perspective. So that not only single Go routine gives a lot of importance on a thread. It doesn't monopolize on one single Go routine on a OS thread. It distributes the work. It ensures that all Go routines run seamlessly. Uh, that is how uh, it works. This is all about the basics of threading. This is all about basics of threading. Okay, so hope you understand what exactly the Go does with respect to the concept of threading.